Hey everyone, this is Andrew. My project mainly revolved around web scraping and how to build and organize a dataset using a platform's provided API. So there's this dataset of a bunch of chess games on Kaggle created from an online chess platform called Lichess. The set was created around 7 years ago and was last updated 3 years ago. It's unique in that it has a count for each type of error each side made during a game. I've used it for a few projects in the past, but for this project, I wanted to learn how I could create an updated version of this from scratch. Lichess provides an API, essentially an interface for people to query data instead of scraping the source code, so I first had to get well accustomed to its documentation website. This is the algorithm for my scraping code. I feed it a list of existing team names from Lichess. It gets the first 500 team members from a team and puts them in a list. Then, for each user in the list, it takes their 10 latest games. Those games are then processed into relevant data and put into a data frame. The processed data part is where I also count the mistakes. Then it keeps looping back and forth until it goes through all players in all teams. This is what the code for getting a user's games looks like. I need to set those 3 specific parameters right here to true to actually get commentary in the data about player errors. And because part of the data is in portable game notation, the chess notation used, and not JSON, I have to receive the information as pure text. I then try to catch every possible networking error down here in the second half of the code. Because if I don't, Python will just error and stop the program. I didn't know I had to do this beforehand, so behind each of these errors was me running the code overnight just to find out the next morning that a networking error stopped it. In response, Lichess began to temporarily block my Wi-Fi from connecting to its website in random 10-minute increments, essentially taking chunks out of my data through the process. As a result, what should have been 30,000 data points became 17,000, but that's okay because the Kaggle dataset is around 18,000, so I'm still similar in volume. If a roommate was playing chess during this time, too bad. So this is the portable game notation format that I was talking about before, abbreviated to PGN. Each cell within the moves column of my dataset looks like this. Every white move is preceded by the move number with 1 period, as seen highlighted in blue, and black moves number has 3 periods. As a result, if we find an error, like this mistake over here highlighted in red, we can trace backwards to find the move number to find which side did it. In this case, it was black's 7th move. Because the format has so much going on, this regex pattern down here was the only regex pattern that actually worked. I tried splitting it up, doing all different types of ways. This was the only thing that actually worked for me. As mentioned before, the data was imported as pure text, and thus I also had to manually regex everything else. The result is a dataset that looks like this. Starting with the more simple stuff, I did some statistical testing with the data. Historically, evidence has shown that the white pieces have an advantage, so I conducted a 2-sample z-test and did find significant data of this. I then divided the data into lower and higher elo games and did 3 2-sample z-tests on them for total inaccuracies, mistakes, and blunders, and found significant evidence that higher elo players made more inaccuracies, but lower elo players made more mistakes and blunders. This was actually different from the same test conducted on the Kaggle dataset, which found evidence that lower elo players made more of all 3 types of errors. This is also the data distribution of the win rates within my dataset. I then conducted logistic regression for predicting the white pieces winning and got an accuracy of 0.79. Blunders were the best predictors, followed by mistakes, and then inaccuracies. Since that is the order of each error severity in chess, this does make sense. They were all significant statistically. I added the standardized average elo of each game as well in there, but that didn't really seem to matter. I also did the same with the neural network. I tried 3 and 4 layers and played around with the hyperparameters, and the best I could do was around 0.78 to 0.79 as well. I did an 80-20 test set split. So a certain famous transformer has recently been causing an uproar due to its innovative way of playing chess.
ChatGPT did not develop its bishop, but rather played the move short castle, capturing its own bishop. ChatGPT plays e5. It skips its own turn. ChatGPT plays the move pawn from non-existence to d6. ChatGPT turned a white queen into a black queen. It was like, nope.
So I wondered what would happen if I tried feeding in the entire game notation data instead. We've already done similar with actual text, like the Fetch 20 news groups. Each text does contain the game result at the end, so I filtered those out of each game before feeding them in. As can see right here, black resigns 1-0. I first used a vectorizer to transform the text and fed it into a 3-layer neural network. This actually worked pretty well and got the highest score of 82%. I then used tokenizer to transform the games for the transformer, and it did the worst out of everything with 0.67, though that's still higher than the actual distribution of wins in the dataset. So with the time I have left, I could still try one-hot encoding the opening codes of games, which I do have in my dataset, and add that as another variable. Try splitting matches by close versus far elo disparity and explore that. I could apply multiple regression, so I could account for all 3 types of game ends. Or I could extract total number of moves per game and analyze that. I could also try grouping games by time control. So yeah, that's my presentation. Thank you.